I'm delighted to present our next speaker, Jonathan Julian Huerta Munive. He's from the Czech Technical University in Prague, and he's going to tell us about the DeepIsaHOL progress report. Take it away.
Thank you. Yeah, well, thank you. I want to present the status report on the DeepIsaHOL project. So what is it? So the general objective is that we want to create tools that serve both the machine learning community and the interactive through theorem proving community for advising the state-of-the-art in both fields. And I come here as a user of interactive theorem provers. So before working on this project, I was doing verification with ordinary differential equations in Isabelle. And then I was looking at all these cool projects that you're doing, guys, and I said, okay, why is all this automation reported in the papers not already in use for ITP users? So I decided to start writing some things so that these tools are more rapidly available for ITP users. And if you're going to take anything from this presentation, is just that this is an open project, so all of this is available online. And yeah, I'm looking forward for collaborations. An example that recently happened was Cheng Song Tan, a collaborator of mine. He was having trouble with Isabelle, and he just said, yeah, can you help me with this automatic repair of proofs? And yeah, I was pointing him to other tools, but eventually he looked at my libraries and he decided, you know, let's work together. And then 4 months later, we had this paper accepted. So if you have any interest in working with Isabelle, please contact me. So now let's go ahead to the presentation in general. When I received the reviews from the submission I placed, the reviewers wanted some general discussion of previous machine learning plus ITP integrations, what can be learned from these previous tools, and then what's the project about, what have we developed so far, and what is there still to do. So that's going to be basically the flow of the presentation. So before that, for those of you who do not know the Isabelle Proof Assistant, or in general the ITP proving experience, basically you have a statement that you want to prove. And after writing each statement, you see some proof obligation that you want to prove, and then you say, well, this is an existential quantifier. I'm going to provide a witness, and I'm going to use a tactic that provides witnesses to existential quantifier. And then that gives you some new proof obligation that you have to tackle. You keep performing this exploration of the proof states until you reach to a point maybe that you say, well, this is so easy. This probably has already been solved in the libraries of Isabelle. I don't know the theorems. I'm just going to call Sledgehammer here, and Sledgehammer is going to call all these external automated theorem provers that will find. We'll try several combinations of the libraries of premises that Isabelle has. And then they will throw some that work for the proof of the current proof obligation, and then Isabelle passes it through its trusted prover. You continue performing this iteration until you get to a point where when Isabelle congratulates you and tells you, well, yay, no subcalls. That was an apply style proof. In Isabelle, we can also do this kind of scripting type of proofs that would resemble more like what a mathematician would write maybe in a piece of paper. So here, instead of doing the apply rule with the existential quantifier, the user can provide the witness and then say, well, this thing that I just defined satisfies these properties. and therefore the conclusion follows. And each one of these intermediate steps, you can consider it could possibly be a call to a sledgehammer or something that an experienced user could replace with theorems that she or he knows for the Isabelle library. Okay, so basically what you will want to do is automate a subsection or the whole proving process with these machine learning approaches. So what I'm going to talk about now is describe two approaches in detail that will give us more or less what people, an overview of what people have tried. And then I will pass quickly through other approaches that are not covered by these two examples. So one of the oldest approaches that we heard about in Joseph's talk was about the k-nearest neighbors algorithm used in tactic-toe. Basically, you look at the proof state and then let's call this proof state phi, and then you create a table of previous proof states and the tactic that was used on them at several points. And you define some metric that will allow you to calculate certain distance between those obligations and the current obligation. And this distance will, like you want the closest one so that you can classify which tactics are the most likely to succeed for this goal. Then you reorder your table, and then you apply this tactic, and then you again use the metric to know which arguments to provide to your tactic. And that's enough for you to suggest the next tactic. And then with a combination of these with some kind of tree exploration techniques like Monte Carlo tree search, they were able to reprove 66.4% of 7,000 theorems from the HOL4 standard library. So this is the main idea. You have some machine learning that allows you to select a tactic, select premises based on the current proof obligation, and then you explore the proof tree. More recent approaches, what they are taking advantage of is the LLM explosion. So one interesting approach was, well, there's not enough data in these theorem provers to generate to train our LLMs. So what we're going to do is just train on human mathematical data. We formalize that to LaTeX, then we provide with this LaTeX sketch of the proof. We're not going to provide the premises. We are just going to mark here's some token that has to be replaced. And at those places, we can call sledgehammer to complete the proofs. An alternative is, well, let's maybe do premise selection with the LLMs. And the idea is that, well, all these external provers, they are just doing premise selection for Isabelle, and Isabelle is the one that is reconstructing the proof internally. So maybe we can provide a neural network approach that finds these premises for us. And they have some nice architecture for the LLM. It's not simply just using your LLM to filter premises. It's actually training your LLM so that an operation on the proof obligations and the tactics separates your more likely premises to work from the ones that are not relevant. If you combine the approach, as I said, they are calling his sledgehammer. If you replace this with Magnus hammer, they have a benchmark where they were able to complete the proof for 71% of 130K Isabelle proofs. So some approaches that are missing from what I just discussed. So there has been some approaches in the HOL4 about doing reinforcement learning. They claim an 89% success on a test of 268 problems. The tactician for Coq, I think, is one of the more investigative works, in the sense that they do implement KNN, graph neural network, and they compare it with an LLM, and they have some nice graphs of what are the strengths of each approach in different settings. And finally, the HOL list environment and LinDojo for Lin, like their project is about retrieving data from these provers, training models based on the data obtained from the provers, and improve the proof completion. So for this, you often also need some interaction with the prover, and that's basically what here in the DeepIsaHOL project we're trying to do. Yeah, so as a brief summary of what I have just described, so we have all these kind of tasks that we can do. There are many more that have been tried. This is not a full analysis of all the literature, but we have premise selection, reinforcement learning, next step prediction, and auto-formalization. And since here we are focused on Isabelle, then we want to complete this row. Okay, so lessons learned. For me is that after reading the literature, I see that language models were not enough for full automation in theorem proving. And what often makes this next step suggestion models to perform very well is when authors tackle this premise selection problem that takes them as far as 50-60% of their own benchmarks. Another approach that also is reported to have huge improvements is just scaling your LLM so that it memorizes, just using one of these LLMs that have consumed the internet, and then using them for suggesting these next tactics. So what we need is more work to compare all these approaches. And so this is where the project starts. What have we generated so far in the DeepIsaHOL project? Well, I also have this tool for you to just write a simple command, and then you can retrieve a lot of Isabelle data. We'll see its shape in a way in some minutes. And you can also do it interactively. If you launch your Scala or Python REPL, you can define a writer object. You can define your theory file or your working directory that has a root file that organizes the different libraries of Isabelle, and just write all the data from that directory. So what does this algorithm do? It traverses your theory file. It detects which ones of these are proofs and which ones are not. It finds the proof, and for each proof, it checks these Isabelle defined steps, which basically you can think of them as command plus arguments. And it retrieves a lot of context-specific information from this step, because not all definitions are useful at that moment. So we retrieve all the definitions that. So we recollect all the theorems that were needed to complete this proof. Also, a term representation of your proof obligation, some keywords that are available for the Isabelle user, because the Isabelle language is context dependent. So these kind of type commands are often changing for different projects, and also the proof methods that that the user needed at that point. So what this has in the special thing from this approach is that we found more lemmas per theory file than in previous Isabelle focused approaches, because there were some proofs about function definitions and type definitions that were not covered before. And as I said, this is more context-aware data. Another contribution from the project is the simple REPL, a readable print loop. It's both implemented in Scala and Python. Basically, you define your REPL, define the logic where you want to start working, where a logic corresponds mostly to AFP entries, and you state your theorem as here is a Python script. And you ask your REPL to apply this Isabelle action. The REPL will reply with a string that is now your new proof obligation. You continue doing this, and you can complete proofs inside this REPL. I also have functionality for you to, once you have completed these proofs, you can recover it and send it to a theory file that has all the adequate imports so that you can check that it's loading appropriately with Isabelle. So to test that what I was doing was working correctly, I did a small scale experiment. I trained very small language models. These are decoders. And these were publicly available by Google, and I trained them from scratch. Basically, this version is just a T5 small model trained from scratch, and I also wanted, like, when discussing with many Isabelle people, they were always suspicious of, well, this fine-tuning process is this really sound? Aren't all the LLMs learning all this data from the internet? So I found this the T5 small model. It has been pre-trained on some data, but it's not focused on Isabelle. So I compare here the pre-trained version and the fine-tuned version, and the data that we supply is for here. For this one is just the Isabelle proof up to that point, plus the user state. For this version here is the Isabelle proof up to that point, the user state, keywords, and theorems that were useful for the user. I was expecting to see some kind of premise selection from the models, but it apparently was not enough. And I also increased the size of the LLM, and I just wanted to see how they were behaving. And as you can see, we can make a lot of metrics about these models, and many times the improvements would look like they are not really improvements, but once you go to the metric of how many proofs they actually completed, you can see that all these different changes that people do for the LLMs, they do help in the proving process. This is an ongoing small-scale experiment. I could add different things to measure here. So next steps. So since from the beginning I told you the interest was on generating useful tools for people that worked with ITPs. So now my objective will be to construct the Isabelle site so that it can retrieve information from these models. as I said, we can continue this small-scale experiments. We can vary the model architecture, change from encoder to decoder to encoder, use one of the latest optimized models, change the data so that the model is actually trying to learn premise selection or doing conjecturing, as we saw in the previous work. And actually, when I submitted this project for funding 4 years ago, and I started 2 years ago, the whole objective was to try to do reinforcement learning. So that's the priority now. And as we have seen from the analysis of the literature, cleverly engineered premise selection goes a long way for doing automated theorem proving with machine learning. So some discussion on why Isabelle was chosen. Well, I was an Isabelle user. That's the main priority. But we can also argue that the ISAR scripting language is close to the natural language, so that might help the LLMs transform, do the auto-formalization steps. Also, Isabelle, we have a nice benchline to compare to, which is Sledgehammer, which is widely used by the Isabelle users. It has one of the largest repositories of proofs, and it's still growing in numbers of users. These are reported in the page of the archive of formal proofs. Yeah, this repeats the point about the premise selection. This is an open project. I would love to see some messages from you. I want to try this in Isabelle. Let's do some nice research together. You're all invited to collaborate, and here's a link to the repo. It's still ongoing, some bugs, but we're working on it. Yeah, I think.
Questions? Okay. I have a question for you.
Yeah.
So, are you planning on any support for larger scale search? Because it seems like a lot of the more recent methods in this area, they have really benefited from just scaling up the search using clusters.
Can you?
So you mentioned search algorithms as being one part of the directions where you're going to go. So have you thought about, or have you experimented with sort of how to distribute the search, or how to scale up the use of this kind of infrastructure?
Not yet. As you see, this is a one-man army project.
I guess that's true.
And right now I have been focused on making things work. The scaling experiments are still there for future work. Yes.
Cool. Well, thank you.
Yeah.
Let's thank you.
Okay.
Okay. So
Our next speaker is Andrei Kozyrev, and he's from JetBrains Research, and he's going to tell us about CoqPilot, which is a plugin for LLM-based generation of outputs.
yeah. So once again, hello everyone. I'm Andrei Kozyrev, and I want to tell you about CoqPilot, which is an LLM-based code generation plugin for Coq programming language. And we have been working on this project in a team with Gleb, Solovev, Nikita, Khramov, and Anton Podkopaev at the Programming Languages and Program Analysis Lab at JetBrains Research. So a quick disclaimer is that this presentation still uses outdated Coq naming, but it will someday change. So let's begin. Since 2022, OpenAI has drastically changed the way we programmers write code. We have gotten used to using AI assistants to produce it and can't live without them. And now even a user not familiar with technology can try to use an AI assistant to produce code. So let's take a closer look at the pipeline of code generation using an AI assistant. First, we write specification, and of an importance is that the specification should be precise and unambiguous. And once the results are obtained, we should check if they coincide with the specification. So we aim to make the programmer seamless controller of these LLMs with as little as configuration parameters. So there are studies that show two things. First, people who use AI assistants tend to introduce more bugs and vulnerabilities into code than those who don't. And secondly, usually people using AI assistants are overly confident about their code being more secure than the latter. So as simple as that, the key takeaway here is that we need to somehow verify our generated code. And we are mainly focusing on Coq, and we are focusing in particular in generating Coq. So in Coq, one writes this specification. What does he want to achieve? Writes the specification, the theorem mainly, and the proof for it. Of particular importance here is that obviously we get a native and a seamless way to check if our proof or code is correct. And when the proof is finished, it could be extracted into an executable, which helps us to write programs in this manner. So for those of you who are not familiar with Coq, I will take a minute and show you the setting. So at the left, you can see the sort theorem, and the proof for it. On the right is the proof state, which is being dynamically updated when I continuously apply so-called tactics and modify the proof. So you can see it updating, and once I complete the proof, I could extract it and apply it to an unsorted list and get it sorted. So a common way to prove a Coq theorem would be obviously first to write a specification, and it's once again the theorem that states that if we take something as an argument, which is a list, we can yield such a type that is also a sorted permutation of the input list. So to write the proof, we firstly, the common setting would be to write the high-level structure of the proof and sketch the main steps and leave some blank spaces, which in this case would be the special tactics admits. So if we go back to our scenario, here you can see some blank spaces, some admits in the proof of the third theorem, and it's basically just a tactic that allows you to give up on the subtree and move on with the rest of the proof until you want to finish it. So this is basically the scenario we are considering. The user leaves admits in an unfinished proof, and we automatically substitute this admits using our proposed plugin. So disclaimer number 2, unfortunately, I cannot control from which moment to give start when I click the next slide. So sometimes I'm gonna play it 2 times maybe. And here I find it kind of beautiful how it substitutes pretty fastly. And you can proudly define after everything is complete and extract the executable. So let's now dive deeper into how our plugin works under the hood. So on an example of one single admit, what do? We analyze the file where it was ran and collect useful information such as already proven premises, proven theorems, combine it with the information with the proof state which was extracted at the point of the admit, and send to a bunch of services that can generate completions. So along with chat-based services such as OpenAI, DeepSeek, JetBrains AI platform, LM Studio, via which you can run any model locally. We also support anything that could be run via some special tactic, like Tactician or Cockhammer. And back to the pipeline, we collect proof candidates and send them to Coq Proof Checker, some proofs contain errors and get rejected, but when a valid proof candidate is found, it is substituted into the user's UI. So now let me walk you through the core features we propose mainly, and what was our main focus is a single button experience. Here you can see everything you need to keep it running. So you just install the plugin, you try to generate something, you get an error that you need to plug in the API key, you plug in the API key, go back to the file and hit generation, and it's done. So it's a dumb example, and it's substituted just for an auto, but it's enough for demonstration, I guess. Also, we have been working on a user-friendly UI, so it handles such errors such as token exceedances, such as rate limits, token limits, unavailability of services, and so on and so forth. And we present it to the user in a adequate manner and give hints on how to solve the problem. So if you have been working yourself with, for example, OpenAI API interface, you know that there are some, if you want to a high load of requests to an API, sometimes you can get some inadequate errors. Also, our model, our settings and the parameters of the models you are using are highly configurable through settings. And a good example here, which I would like to tell you, is such that, so sometimes you may want to use, for example, a sequence of models. You want to try some predefined tactic, then you want to use a cheap model, for example, DeepSeek model, and then if it doesn't work, you want to fall back to a stronger model, for example, O1 model from OpenAI, and this is all possible. You just sketch a list of configurations, and CoqPilot falls back through the list until it finds the solution. So, and most importantly, we position ourselves as an experiments framework, and for this reason, we have been working on such things as that you could easily add your generation service, or maybe you can ask us to do that, so that also on higher configurability and easy experiments. But the main theme of this particular talk is the benchmarking framework we were working on, and for this reason I would like to go deeper into it. So let me state the problem here. What are we trying to do? So we have a bunch of Coq projects, and we want to take a subset of theorems from these projects. So that's going to be our targets. And we want to measure performance of different models with different configurations, with different parameters from different services on these targets. And maybe you want to compare the same model with different temperatures. Maybe you want to compare different prompts, different services, anything. It would be possible in our framework, and we wanted it to be done easily. So as an output, we would like to get kind of a matrix of performance of each and single model on each target. So quite reasonable. What do we do to solve these problems? First, we provide user-friendly DSL input for the setting of an experiment. Secondly, we parse the data set and all the targets we have, and also we use caching of the data set, and I will talk on this a bit later. And lastly, we execute tasks asynchronously and achieve great performance in terms of speed and correctness. So once again, about the features, but in more detail. Here on the right, you can see the DSL we provide. I guess it should look kind of neat. You specify the project you're using and the build system you need for it. So you can specify the subfolder, you can specify the file or some specific set of theorems, however you want it. you specify the targets you have, and then the services. Once again, the service, in my terminology, is just some specific API provider, as like OpenAI. You specify the service, you specify the non-default parameters of the models you want to use, and yeah, if it still looks kind of tricky to you and frustrating, then we just have a template on the GitHub. Asynchronous tasks. So we measure the performance. We execute tasks asynchronously. So each couple between the model and the target is one task, and we execute them asynchronously and get performance boosts, performance efficiency of roughly 4 times in comparison to sequential execution, which is nice because sometimes you may have a benchmark experiment running for 4 days or something like this to check like 5,000 theorems on 5 different models. Obviously, we have all the necessary synchronization, and all of the resources are being shared correctly. And now let's go to the main feature, the main idea behind the benchmarking system that we had in mind while developing it. We allow experiments of all sizes, and yeah, there is an idea that benchmarking and experimenting is always about large-scale experiments, but we think a bit others. So sometimes you want to run a quick experiment until you run an experiment on 5,000 theorems. Sometimes you want to check something, test that everything works correctly, that you like the parameters, and so on and so forth. So what do we do to allow small preliminary studies? The DSL, about which I already talked, and you specify the experiment setup through the DSL, and then just hit npm run benchmark, and it's done. We allow dataset caching. We generate visual human readable reports for fast analysis after experiments, and implement a fast fail strategy and logging, so that if on the small scale, when you want to just check something and not wait until all the experiment is done, you can find out that something occurred wrong really, really fastly and easily. So what about large-scale experiments? We're focusing on reliability, that nothing gets lost, obviously. Secondly, we covered all of the problems that I already was speaking about, that token limits, connection issues, so on and so forth. You have an experiment running for 5 days and nothing goes as planned, but we tried covering as much as we could, as much as possible. And also, we live in an unpredictable world, so your machine could die or something. We implemented the feature to resume benchmarking, even if something went completely wrong. Also, we can collect extensive data throughout the whole run to analyze it afterwards. Now, let me briefly tell you about the evaluation we have done to assess the efficiency of the provided features, and just to which experiments we were running. In addition to, maybe you have seen this table, we have it in our ASE paper and somewhere else. In addition, what has changed since that time? We have benchmarked on the O1 model, and it showed great performance and great improvement in comparison to GPT-4o, but it was not as good as Cloud 3.5, which was dominating O1. Also, we have benchmarked on the DeepSeek R1 model, which showed comparable performance to O1, but for a magnitude lower price. Apart from evaluating different models against each other, we evaluated different context selectors against each other. So obviously, sometimes your context is limited, or you want to use only a quarter of tokens, maybe you are limited on budget or on tokens. So sometimes you need to do some context selection, and we related. You can also implement different ways of context selection easily in CoqPilot, and we evaluated two context selection metrics against each other. The first one is dump; it just takes the closest to the target theorems from top of the file, and the second one uses frequency-based analysis between two statements. And if we take the distance metric for the kind of full context, or maybe the whole file, so on average 40 theorems in context, we got the performance of 40% on some other data set. If we reduce this number to a 7 just a constant, some nice looking constant, not too much, not too many, not too little, the performance drops to 28%. But if we compare it to 7 premises chosen by Jacquard's context selector, then we achieve 40% performance once again. Yeah. And it's almost it. Let me briefly go through the features we have once again for the last time. We already support many chat-based completion providers such as OpenAI, DeepSeek, JetBrains AI platform, and local models via LM Studio. You can also plug in Taxation or Hammer easily via tactic-based providers, and we also working on generalizing the way you can add some additional proof provider to us. We added a possibility to benchmark against recent paper Rango, and we are running an experiment right now. We wanted to finish it till the talk, but unfortunately we got some problems with the machine. But we have done all the engineering stuff, and we hope that it would be really easy to add any other generation service to us and benchmark between different models, different services in a user-friendly model, in the user-friendly mode. Everything you need to, all the conditions you need to. All the conditions that are on the proof provider that we are integrating is just that we need some reasonable API of interaction between us and you, and that everything is built in a virtual environment, so we can run it on a user's machine easily. And yeah, thank you so much for your attention. We are developing project and would love to hear your feedback, and we are always open for collaborations. This is all in all the summary of what have we accomplished, and yeah, thank you so much everyone. I'm open for your questions.
Questions?
So can you take that example of permutation? I mean, that example of permutation predicate which you used? Yeah, so like, is it the one that predicate you've defined? Is it the one from the standard library?
No.
No. Okay.
Thanks a lot for the very nice talk. I was wondering, on your benchmarks, you are testing on existing projects like CompCert and IMM. You are not worried about data contamination?
Yeah, we are. It's an open question. Yeah, we are. I guess I was curious about your talk and your benchmarking on EB4 project. And you said that there are less chances that it was seen, but I guess it is the OpenAI models are being reinforced every day, and I guess the chances are quite big in both cases, and it's an open question. We have been thinking on it for some time, but we just, probably it has seen something,
Okay, and just one other question, if I may. So the bottleneck is not running the model. Sorry, rephrasing. So the bottleneck in all the computation, is it the ROC interpreter, or is it asking the model to generate an answer? And are you running the ROC interpreter on the user machine, or is it running multiple instances everywhere?
Everything on the user's machine. Coq interpreter on the user's machine. We communicate with CoqLSP. And
it's just one ROC interpreter for all the...
No, we are creating multiples.
Okay, thanks.
Multiple instances,
Any other questions?
Perhaps a very naive question, but how do you prevent the model simply saying, "Okay, well, admit again"? Right? Is there anything preventing that?
No, kind of. We just parse the answer and check that it does not. So that's
sure. That makes sense.
Any other question? So I have a question. So suppose your goal is to do verified software development, but in a different language. So let's say you're doing it in C, and you want to extract the code out of your Coq proof. So is there any plan to support this sort of development in the longer run? Because that introduces these extra complexities that, you want to connect the C code to the Coq proof and so on.
So once again, you are extracting the Coq proof into
C, but then, maybe you're modifying the C code as well, right? I could imagine a workflow like that, which has some implications for the proof. And then, this sort of Coq and C co-development, right? Which would often, I would imagine, arise in these more verified software development settings.
I guess it's more of a question to us.
No, Coq already supports that, right? But it's more whether or not the interface has. So is your interface designed to support this sort of verified development? Because Coq, one of the big capabilities is that you can extract the C code and then you can.
But we are just generating Coq. Why do you think that we are we are the bottleneck to some?
No, I don't think you're the bottleneck. I think it's more of a question that, is there any plan to, I can imagine using your kind of interface to make verified software development in, some kind of a target language, much more effective, right? Much more scalable. But that would presumably require, connecting the proof development process with the program development process, right? Which is, it seems like, that's an opportunity that's waiting to be taken. Okay.
I can see your point.
Okay, but there's been no discussion at this point of. Okay, cool. Okay, thanks. All right, thank you.
Thank you so much.
Okay, our last talk of this session is kernel-level expression generator, and it's by Petrovčič.
Thank you. So hi, I'm Ljub. Hopefully you can hear me. And I'll be presenting our kernel-level expression generator. So in our work, we designed a generator of expressions in lean-force formal grammar that are well-typed. And first, I just want to walk you quickly through lean-force pipeline of how the code, which here is in the input, is parsed and type-checked. So the input comes into the parser, and it's parsed and then expanded and given to the elaborator, which actually generates this low-level kernel expressions that are then passed on to the kernel to see if they are well-typed, so correct, or ill-typed, so incorrect. And really, what we wanted to do was to generate at this level where the syntax is very simple. No, but why would you want an expression generator of, so a generator of well-typed expression is that in whatever you want to do in math and AI, you need good embeddings. Good embeddings, effective embeddings are key if you want to do premise selection, whole completion, theorem proving, whatever. However, neural networks need a lot of examples to learn effectively. And so we tried learning on Lean4's MATLib, which is quite a big library, but it turns out that it's a very dense, very complex data set where simpler examples of how to use basic structures are neglected, and thus this is not really good for training a neural network. So really we wanted to create a generator of these simpler expressions that could be then used for training data. Now, what are well-typed expressions? Well, well-typed expressions are raw expressions coming from Lean4's raw expression formal grammar that satisfy all the rules of Lean4's type system. And these rules impose a very strict structure on these raw expressions, making well-typed expressions pretty rare. Another layer that I'll be mentioning is definitional equality. Is that this is going to rely on reductions where expressions that appear dissimilar might end up becoming definitionally equal. So when you want to create an expression that satisfies all these rules, you also have to take into account this additional the definitional equality. So the first question is, well, how can we find these well-typed expressions? And as our baseline and the obvious approach is to do some kind of brute force search, where you would uniformly sample an expression and then test it against the kernel to see if it's well-typed or not. You could also do some sort of constraint search where you would traverse the space of all well-typed expressions in some clever way, but we didn't really know what is a clever ordering to actually find all these expressions, and also how to restrict yourselves to expressions that satisfy all the rules that wouldn't require a lot of manual labor to actually implement make a system where these rules would be satisfied. So really we turn to reinforcement learning in order to let the model and the framework take care of all these details. And in order to do so, we had to operate in an environment that would check these expressions. So we rewrote the core type checking, the core of Lean4's kernel into Python to extract all the information from the kernel to provide rewards, and in order to fully integrate the kernel into our reinforcement learning environment. Now the next question is, well, how can you even build an expression which is a tree? And so for this we chose to build it in a pre-order fashion. So we start by building the root, then we're building the left child, and then the left child, and so on, before returning and back and building the right children. And this is really complementary to the way the kernel operates in. So the type theorists might call this structurally. It's so it traverses the expression structurally, checking the sub-expressions before returning back to a node and checking that the rules for that node are satisfied. And this really avoids delaying type checking, which is linked with giving rewards in our environment, and you want to, in reinforcement learning, you generally want to avoid delaying rewards. I should mention here that we restricted our model to only use a small set of constants or declarations, as Lean calls it. So these are basic structures with which the model, the agent, is going to operate in this environment. And so the initial idea was to give rewards for well-typed sub-expressions. So these rewards can get, so these rewards are denser. And this would be an example of how our agent operates in our environment. So you start with it starts with a hole, and its action consists of choosing a constructor from lean force formal grammar. And so in this case, it would choose the function constructor. And then it would the environment would query it for the left child. What is going to be the constructor for the left child? And in this example, it's going to be for example, the agent chooses that this is going to be a sort of level 1. And at this point, the kernel can already check some parts of the partially complete expressions and give the reward for at least for this part. And so now it returns back to complete the right children. And for example, this is going to be the De Bruyne index. So the model chooses as an action, it chooses that it's going to be a De Bruyne index. And since this is actually an expression representing the identity function, this expression is correct, so well typed. And thus the kernel can reward these two nodes since they satisfy all the rules and give the rewards to the agent. But we don't want our agent to build just well-typed expressions. We want, if we're going to use it as some sort of training data, we want some diversity, some creativity. We don't want it to just focus on using some of the constants or converging to just using some of the just one constructor, for example, in lean force formal grammar, since then that is not interesting. So we decided to amplify rewards for longer expressions, so those that are not just 1, 2, 3 words, but we want them to be longer. We also wanted to reverse some sort of diverse use of the constants and the constructors. And somewhat antagonistically to the first point, we devalued rewards based on the depth of the node. Because you don't want the model to just generate infinitely deep and long expressions that never terminate if this is going to give it those large rewards. Now the next choice was the choice of model and how to train this model. And for this, we chose something that could operate on sequences and adapted them to work on trees and dogs. And now I should mention that in Lean, these expressions are not actually represented by abstract syntax trees, which we learned the hard way, but they're actually represented by rooted dogs, so directed acyclic graphs, due to since some of the sub-expressions that are identical are merged in order to save memory, and this is an optimization that Lean uses. Now, for a reinforcement learning algorithm, which shows the classical reinforce that directly through gradient ascent maximizes the cumulative reward. And so this led us to, this worked in, at least what we thought worked well, to a model that could generate expressions that were slightly longer, so 12 to 16 nodes, and it could use some of the constants and some of the constructors with at least a non-zero probability. And so this is a graph showing the percentage of how many of the expressions the model generated in a batch were well typed. And so this increases with training, which you'd hope that it does. Now this is a similar graph, but now on the on the y-axis we have the average length of the expression generated in the batch versus the batches, and so this also generally increases. But now here we came to the problematic part, in that we observed how many of these well-typed and on the y-axis, I now have well-typed sub-expressions, since this turned out to be a smoother metric, because these reinforcement learning graphs can get quite chaotic. But now here we observed that the model is going to start reusing expressions, and so these expressions that it generates are going to keep repeating. And so in this metric, the model performs worse than the brute force baseline. Now, and this really led us to to the core of the problem was our reinforcement learning setup, in that the agent is going to maximize the rewards which were given for if the expression generated was well typed or not. Then it would try to find an expression that would maximize this reward. And so this is going to make it very difficult to create a reward system that would actually encourage creativity. So we were driven to not only using extrinsic rewards, so those that are given by the environment, but using some sort of intrinsic approach, where we would be driven by the agent would be driven by rewards given intrinsically. So now in this setup, the model is actually going to gain an additional role beside being the agent, in that it is going to predict if what it generated is going to also be well typed. And so to do this, we introduce some real metric of how well typed the expression is going to be, and then the model is going to try to predict this metric. And for our surprisal end, here I'm citing a paper on which this surprisal is based, but I should know that this formula here is heavily modified and simplified to what they use, in that we're not going to try to find expressions that have this that are very well typed. It's more that we're going to try to find expressions that are surprising to the model, that are surprisingly true to the model. It didn't expect it to be correct. And so now we're going to encourage states. Now we're going to encourage expressions that are going to be surprising to the model. And so now the new objective is to maximize the cumulative surprisal of given by the model to itself. And here a secret bonus that I'll demonstrate later is that there is now no need to shape the rewards for previous objectives beside well-typedness, and I'll demonstrate this on a graph later. And as is standard in reinforcement learning to encourage exploration, we also added an entropy term based on the policy to further encourage exploration of the agent. And so now the final loss is going to be minus the surprisal, since we're trying to minus the surprisal objective, since we're trying to maximize it, plus the term that is going to train the model to evaluate what it generated is going to be well typed or not. And now the final is going to be the entropy regularization term that is going to aid in exploration. And so now if I return to the previous metric of how many expressions the model generated are going to be, they're going to be new, that it hasn't generated before. And so our model here trained with surprisal is going to outperform both the baseline and the model that was trained on the regular extrinsic rewards with reinforced algorithm. And I should also note here that the entropy regularization term was added to the previous reinforced algorithm, so this was not the key change, right? The surprisal was really what made the difference. Now, but are expressions that it generates meaningful? So, and this is what turned out to be a problematic approach. So these expressions are correct, but are they meaningful? And one approach that we could think of was, well, can it find sub-expressions that also simultaneously appear in MATLib? And here is the graph comparing the percentage of how many of the expressions the model found that were also present in MATLib and were and these expressions contained only the constants that we restricted the model to use. And so you can see here that the model performs slightly better than our brute force baseline. However, it should be noted that there is a lot of low-hanging fruit here, meaning that there are lots of very simple expressions that are also present in MATLAB that are very short. So, for example, 1, 2, 3 nodes that also the brute force baseline can find. And so if you restrict yourselves to observing expressions which are of length greater than 8, you're going to find that this difference increases. Now here is the graph I was referring to earlier, where I said that we don't need to shape the rewards further to encourage the model to generate longer expressions, since it's going to now automatically find the shorter expressions boring, quote unquote, and it's going to try to search for longer and longer well-typed expressions. Now, since the model also predicts if whatever it generated is going to be well-typed or not, it acts as some sort of neural type checker for these simpler expressions. And so here we have the graph that demonstrates, so ill-typed examples were examples generated by the model which were corrupted by us manually. And so the model generally learns to differentiate between correct examples, which are old examples from MATLAB, and the negative examples that were corrupted manually by us. And now, so this leads me to the final slide of limitations and future work. And the first and most obvious limitation is the inability to deal with the large amounts of constants that are in MATLAB. So we restricted our model to use only constants. So these are structures that are used in MATLAB, and we restricted the model to use only a small subset of them. But this is going to be problematic in any reinforcement learning approach, as reinforcement learning algorithms generally suffer from large action and state spaces because the number of possible combinations is going to explode with the number of actions. And so really, for the future work, we want to study the impact of the chosen set of available constants that we limited our model to use. Now, the next 2 points are what we initially wanted to do, is to use the model to embed expressions and use them in whatever we, so for anything related to math and AI. And we also want to use it as, we wanted to test it as some sort of adversarial neural type checker. And for our final future work, we wouldn't want to just generate any expression. We would want to generate an expression of a certain type, which would be an equivalent to training a prover in this environment. And that's
okay. Thank you. Questions?
So when you're training surprise OS, do you have a gradient pass-through to the type checker?
sorry.
So can you go to surprise slide?
This slide?
Yeah. So when you do gradient by surprise,
Yeah.
do you have gradient pass-through to the theta in the type checker model?
I'm not sure I get the second word.
So basically, because when you train to maximize surprisal, it can also maximize surprisal by making the type checker model bad.
Yes.
Do you have a gradient freezing here to prevent that?
Yeah, we tried to separate the gradient descent for the type checker and the agent, and this led to slightly better results.
Mm-hmm. Thank you. That makes sense.
It didn't make much of a difference.
Hi, maybe this is an ill-posed question, but like in the 10 years ago, there was a lot of work on generating well-typed terms to test compilers, for example, in the property-based testing community. In particular, writing random generators for checking like a Haskell compiler. And I was wondering if you could use this kind of technology also for these kind of goals?
For Haskell?
Well, in general, for property-based testing, for finding good tests for sparse conditions. So, because well-type terms are sparse.
Oh, I see. Well, yeah. This is really the problem. Really, boils down to finding some not just expressions, but they can be more arbitrary expressions for what I assume Haskell also has, or just strings where you could, if you can always use this approach, since this is a general reinforcement learning approach where you would not rely on external rewards, but you would rely on some of this what I mentioned, the intrinsic reward in this environment. So you can do this approach in anywhere where you discern between expressions that are interesting and those that are not interesting.
So you said that basically the model kind of learns to predict whether the expression would to act like a compiler, and you have shown the graph, but I was struggling to understand what do I get from this graph? So could you maybe in a few words say how well it was performing in predicting? How was performing in general? This kind of.
On the y-axis there's the percentage of examples, and on the x-axis is the model's prediction of if the expression. So -1 is that it's going to be incorrect, and 0 meaning that there's nothing wrong with the expressions, meaning that the expression is correct. If you're asking me how it performs in general as a type checker, I'm not sure how to evaluate it, because I mean you can put expressions from Mathlib and hope that it works, but it's not going to. As you know, I really want to emphasize that we restrict it to using only a small subset of constants. And so in general, Mathlib is going to look like, okay, you have one expression that's going to use just a bunch of different constants. It's going to use a lot of constants that are in Mathlib, and it's going to be hard to feed the whole Mathlib into this sort of type checker. So we didn't evaluate it like I think you are suggesting.
Okay, thank you.
Sorry, may I have a follow-up question about this? Do you have any idea how performance of your neural type checker compares to real type checker?
So this is the graph comparing.
No, I mean like in terms of time or other resources.
Yeah, it's probably slower. One would think. So the point of a neural type checker wouldn't be speed; it would be the direction. So you're not just getting the answer if this is correct or not, but how in the form of gradient you would get the direction where you would want your other model, the generating model, to go.
Makes sense.
Mm-hmm. Thanks.
Okay, there are no other questions. Let's thank you.